All
All right,
right,
recording is on.
thank you everyone for being here for the next edition of the 1W-MINDS seminar. Today we have Dr. Shay Gilpin, who is at the University of Arizona, and Shay will talk to us about inaccurate variance evolution implied by discrete covariance propagation. So Shay, thank you for being here and take it away.
Thank you, Christian. Thank you everybody for attending. Today I'm going to be talking about a part of my research where I'm focused on covariance propagation. So this is the dynamical evolution of covariances that can occur in the statistical estimation of dynamical systems, but is actually something that we encounter every day in the context of weather prediction. And so today I'll give an introduction to this research, and I'll begin with the motivation for this work, which actually comes from weather prediction. So weather prediction is something that we interact with, as I said, on a daily basis. And often we're asking questions like, okay, what is the weather going to be like in a few hours or in a few days from now? In particular, for me, I want to know, well, is it going to rain this afternoon and do I need to bring a raincoat? And so often we answer these types of questions by looking at the weather on our phone, or we can go online. I actually go directly to the National Weather Service to look for these types of forecasts. So this was a forecast that I looked at earlier this morning for the weather here in Tucson. And we can see that it gives us these different predictions of the temperature. And of course, we're under a flood watch, at least for the next couple days. Now, what's quite remarkable about weather prediction is actually we can reformulate this question mathematically. And in particular, we can actually view weather prediction as an initial value problem. And so rephrasing this question, we can actually say, given the weather now, what will the weather be like at some point in the near future? And so as we know, with initial value problems, there are two components. The first component are these dynamical models. For weather prediction, these are partial differential equations derived from our physics-based knowledge and conservation laws that we use to approximate the evolution of the atmosphere. And then the other component is an initial condition. And typically in these big weather systems, the initial condition is taken to be a combination of the previous forecast, so what our models predicted the weather was going to be, and information from the vast observation network that we have from across the world, which includes information from satellites, weather balloons, and so on. And so these two ingredients then form the basic building blocks that we need in order to answer this question, given the weather now, what was the weather going to be like in the near future? Now, if you look very carefully at what weather forecasts produce, not only do they tell you what the weather is going to be like in the future, but they also tell you what is the likelihood of the weather going to be. You most often see this maybe in like percentage of precipitation or whether or not there's a chance of rain. But they do this for the other variables in these models as well. And so for instance, I have an example here of what they do for temperature. So these figures come again from the National Weather Service, where they're giving you plots of this probability or percent chance that the temperature is going to be either above, below, or near what they claim to be the normal temperature for the next couple days. And so we can see here that most of the US is predicted to be warmer than what they consider normal. But of course, right here where I am in Tucson, it's expected to be about near normal. And so what this tells us is that in these weather prediction applications, not only are we interested in the evolution of the state of the atmosphere, but we're also interested in the uncertainty of these estimates. And in these large systems, the uncertainty is quantified in the first and second moments. And so specifically the mean state estimate, but then also the estimation error covariance. And so while it's generally understood that this propagation or evolution of the state of the atmosphere is pretty well understood, we have a pretty good idea of how this works. The propagation of the covariance is not well understood. And so the focus of my research is to really try to understand the evolution and propagation of covariances motivated by these contexts like numerical weather prediction. And so, in particular, I apply theory from partial differential equations to study the interplay between these two problems. In particular, the discrete covariance propagation. So how do we approximate solutions to partial differential equations numerically on a computer, given some numerical methods, such as a finite difference scheme? in contrast with the continuum covariance propagation, so namely the exact solutions to these partial differential equations that govern the evolution of these covariances. And what I'm going to talk about today is that for a class of differential equations that are motivated by these weather prediction applications, there's a very interesting discrepancy between the discrete propagation, so these approximations to these solutions, and the continuum covariance propagation. And this discrepancy is actually quite different than the typical discretization errors that one would expect when applying a numerical method to solve these problems. And that's what I'm going to be focusing on today. And so the class of equations that I'm interested in actually comes directly from atmospheric dynamics and applications such as stratospheric ozone forecasting. And so in these equations, I'm interested in a state Q that lives on the surface of the sphere that satisfies this linear hyperbolic equation given here, where our velocity field V is deterministic and given to us, and then the scalar B is also deterministic and can be different depending on the different applications. So for example, if B is equal to 0, this represents just pure advection, for instance, of ozone along the surface of the atmosphere. Or if B is taken to be the divergence of the velocity field, then this can then represent, say, mass conservation in an atmospheric circulation model. Now, in these weather prediction applications, we introduce the uncertainty through the initial condition. And so in particular, I'm going to assume that my initial state Q naught is random with some mean state Q naught bar. Therefore, I'm not only interested in the evolution of the state, but I'm also interested in these other quantities. So we're interested in the mean state. We can also then go ahead and define a covariance for two spatial variables, x1 and x2, that live on this sphere. And then from the covariance, we can define this other quantity that I will talk about a lot, which is the variance sigma squared. Now, in practice, the evolution of these quantities, so the state, the mean state, the covariance, and the variance, are approximated numerically, again, using some sort of finite difference or appropriate PDE solver. And what I'm going to show today is that the resulting variances that you get from these approximations are surprisingly inaccurate, much more so than you would expect from the get-go when you think about these problems. And so to illustrate how inaccurate these variances can be, we're going to look at a very simple example that again is motivated by chemical tracer forecasting, such as stratospheric ozone, and examples that have gone back to the early 2000s. And so in this context, we're going to take a very simplified approach. We're going to just consider our state Q now living on the unit circle. Our velocity field is going to vary in space, but not in time. And I'm going to pick this, what used to be an arbitrary coefficient b. I'm going to fix this to be 1/2 Vx. And equations like this can arise when Q represents, say, the square root of a tracer concentration, for instance. Now, the first step in this process is to then go ahead and define the discrete state propagation. So this equation here for a vector q then describes the propagation from the state at time k to time k plus 1, where the matrix M represents a linear discretization of these state dynamics in this equation here on the left. So for instance, after applying a finite difference scheme. Now, in this example, I'm going to take a very simple standard approach within the community. I'm just going to do a Monte Carlo approach in order to estimate these statistical quantities like the variance. And in the community, we refer to these as an ensemble approach. But the idea is very simple. I'm going to generate an ensemble or in a collection of M initial conditions, where I'm going to draw these from a Gaussian distribution with a specified mean and a specified covariance matrix that depends on a parameter C that I can adjust, and I'll discuss that a little more later. And then with this collection of initial conditions, I then propagate them forward in time using this discrete state propagation equation to some fixed time. And then at that time, we can just then use sample statistics to then estimate the mean state at that time, and then of course the variance, which is what I'm interested in. Now, what's nice about this simple example that I've chosen here is that I actually have access to exact solutions, not only to the state equation and therefore the mean state, but also for the variance. And so what one can do is by defining the variance in this way and going back to the state equation on the previous slide, we can actually derive an explicit partial differential equation that describes the evolution of the variance, which is given here. And so for the velocity field that I chose, I can compute exact solutions to the variance equation and the mean state equation as well. And in these experiments, I can actually compare these exact solutions to the approximations from the sample statistics I get from evolving this ensemble of states. Now, before we actually look at the results of these experiments, we can actually think about what are the errors that we do expect in these experiments. The first type of errors that you might expect are these numerical discretization errors, which are associated with the discretization that we enforce when we define the discrete state propagation here. Now, I'll just remark here that in these experiments, I'm smart about my numerical discretization, and I rewrite this into an energy conservation form and apply a Crank-Nicolson finite difference scheme, which one can show conserves important conservation properties from this equation. So the numerical discretization errors will be there, but I don't expect them to be very large. Now, the other set of errors that can occur comes from this Monte Carlo approximation, which is referred to as sampling errors. So because we are going to be estimating the mean state and the variance from a limited number of ensemble members, there is an associated error with that estimate. You can think about this intuitively, is that if you're trying to estimate the mean of a set of quantities, of course, if you don't have a lot of quantities, that estimate's not great, but that estimate gets better as the more information that you have. And so that's this idea of sampling error, that there will be some error depending on the size of my ensemble. And so now, with this kind of idea in mind, let's actually look at the errors for this experiment. So in this figure here, what we're looking at is the normalized error in the L2 norm for the mean state, which is here on the left, and then the variance estimates, which I'll show on the next slide. So the normalized errors are given in percentages here on the y-axis, and these are a function of ensemble size, which is given here on the x-axis. And then these three different curves correspond to three different sets of experiments for different initial covariances. So you can think about this parameter C gives you an idea of a correlation length scale, or basically how long these correlations are. So a larger value of C means longer correlations, so kind of slow decay of correlations over distance, which then progressively shrink as these values of C shrink. Now, if we look at the errors in the mean state, the first thing that we observe is that these errors are actually pretty small. They're all generally less than about 6%, which is pretty good. They don't depend on this initial covariance. And what we do see here is this growth in error as ensemble size decreases is very characteristic of the sampling error that I introduced before. This is a well-established fact that as ensemble size decreases, we expect the errors to increase more or less exponentially. But overall, these errors are really small and what we kind of expect to see. So that's true for the mean state, but now let's think about what happens with the associated variances. And so now we're looking at the errors in the variance. The first thing that I want to note is that the scale on the y-axis is actually changed. Before it went up to about 6%, it's now increased up to 50%, so about a factor of 10. And the results are quite surprising. The first thing to note is that the errors in the variance estimates are significantly larger than what we saw for the mean state, even though we're estimating these from the same ensemble. The second observation that we make is that we can see that the errors in the variance are generally constant as the ensemble size decreases. So we really don't see a visible impact from the sampling error as we did in the mean state. Instead, what we see is that the errors in the variance actually depend on the structure of the covariance that we started with, meaning that as correlation length scales get smaller, so these gradients near the covariance diagonal get sharper, the errors in these variance estimates tend to get worse. And so the question is, okay, what is actually going on here? And if you recall, we have exact solutions to this mean state and the variance equation. And what we can do is we can actually look at the solutions that we get and compare them to the exact variance and get a better idea of what's actually going on. And so what I'll do is I'm going to pluck out this large ensemble size of 4,000 members, and I'm going to plot the sample variances, and we can get a better idea of why are these errors so large. So in this figure here, what I'm showing is we're going to be comparing the exact variance with these approximated variances, plotted along the unit circle here on the x-axis. And we'll begin by looking at the exact variance, which is given here in solid black. Now, what I've added here in this figure, these colored curves correspond to these sample variances from this large ensemble for these different initial covariances that we were looking at on the previous slide. And what we can see right away is that these approximated variances, which should all be approximating the exact variance in solid black, are wildly inaccurate. None of these curves capture the exact variance solution, and they're all behaving quite differently. The question then becomes, okay, well, what exactly is going on here? And so it turns out that these sample variances are actually approximating something, and what they are approximating is what happens if you propagate the covariance matrix itself. So in these Monte Carlo applications, we are just estimating from an ensemble of states using sample statistics. But what you can do is you can actually derive an equation that describes the propagation of the covariance matrix directly from the state. So given the state propagation equation and the definition of the covariance matrix, you can derive what is referred to as the explicit full rank covariance propagation equation, which appears in common filters, for example, if anyone is familiar with those. And so what I did here is I actually took those initial covariance matrices, I propagated them forward in time using this equation here, and then I plucked out the covariance diagonals, and then I plotted those in these dashed curves on top of the sample variances here. And what we can see that is quite remarkable is that the variances implied by this covariance propagation in dashed are smooth solutions that match exactly what we get from these sample variances, but again, are not approximating the exact solution to the variance equation and are wildly different. There are regions where they over-approximate the solution and under-approximate solution. And yet, these two different propagation methods that we used to get the variance are consistent with each other, but not consistent with the exact solution. So this gives us an idea that there's something deeper going on here that we need to try to understand. And so in an effort to try to understand, well, what is it that these discrete methods of evolving a variance are approximating, we have to take a step back and actually revisit these underlying continuum covariance dynamics, these PDEs that are governing the dynamics kind of in the background. And so in order to do this, we can actually go back to this advection equation that I introduced at the very beginning. So we have, as a reminder, this is our advection equation. We're now living on the surface of a sphere, and we have a general kind of coefficient in here. And we can define a continuum covariance using the expectation operator here. And with a little bit of manipulation of the state equation, we can actually derive an explicit equation for the covariance that I refer to as the continuum covariance equation. And as we notice, we see that the equation for the covariance is a hyperbolic PDE, like the state equation, but now it's in two spatial variables, x1 and x2. And if we look at this a little carefully, we actually observe that there are some interesting symmetries in this equation. In particular, we see that there are these symmetries in these spatial derivatives here. And these symmetries in these spatial derivatives actually give rise to some very interesting behavior in the covariance dynamics itself. So we can take a closer look at these symmetries, and we know that this is a hyperbolic PDE, so how do we go about solving these? Well, method of characteristics comes to mind. So we look at these spatial derivatives, and we use those to then define our characteristic equations. Now, what we observe here is that these characteristic equations for the coordinates x1 and x2 actually are the same. So they both satisfy the same equation because these velocities here are actually the same velocity. They're just evaluated at these two different coordinates. And so if we think about this for a little bit, something interesting arises. This interesting behavior arises is, let's suppose that we start out with our initial coordinates to be equal. So that these two initial coordinates S1 and S2 are equal. Because these characteristics equations are the same, this means that the coordinates x1 and x2 are actually going to be equal for all time. And so what this means is that this surface, x1 is equal to x2, is actually a characteristic surface for these dynamics, simply due to the fact that these characteristic equations are actually the same. And so this has important implications for solutions to this covariance equation. In particular, if we think about a covariance that is strictly diagonal at the very beginning, meaning it starts on this hyperplane where x1 is equal to x2, well, because this is a characteristic surface, diagonal covariances are going to remain strictly diagonal for all time. Again, because this is a characteristic surface. And so colloquially, what this means is that white noise remains white. Okay, diagonal covariances remain strictly diagonal. And so if we dig into this behavior a little bit more, what we actually find is that this gives rise to two different kinds of solutions along this hyperplane. Now, to see where these two solutions come from, we actually have to recast this problem a little bit, and we need to actually look for weak solutions to this equation. To do this, of course, we would define what I refer to as a covariance operator, P sub t, where the kernel of this operator satisfies this covariance equation here. And so with a little bit of analysis, what we find is that solutions along this hyperplane come in two different forms, and they depend on the structure of the initial covariance. And the first case comes from when we assume our initial state Q0 is spatially correlated. So in this case, we can define our initial covariance to be the product of a standard deviation or a variance function sigma naught and some correlation function that has some non-zero off-diagonal entries. And then we can proceed through the appropriate analysis. And what we find is that the dynamics along this hyperplane satisfy exactly what we expect. Satisfies the variance equation, which is given here, and then the covariance then remains the product of the variance and the correlation, and this operator remains an integral operator. And this is all fine and great, and this is exactly what we would expect. However, we need to think about this case of when the initial covariance is strictly diagonal, because we expect something interesting to happen because this is a characteristic surface. And so in this case, that corresponds to an initial state Q0 that is spatially uncorrelated. We represent the corresponding covariance as the product of a continuous function and one spatial variable only in a Dirac delta. So this will give us that strictly diagonal structure. And then again, hence to why we need to look for weak solutions to this equation because of this Dirac delta here. And so through very careful analysis, we actually uncover a different set of dynamics. What we uncover is that the covariance remains the product of a continuous function in a Dirac delta, where this function PC satisfies this new differential equation here, which I refer to as the continuous spectrum equation. And this equation is so named because solutions to this equation actually define the continuous spectrum of this corresponding covariance operator. And so what we can observe, which I've highlighted here in blue, is that for divergent velocity fields, which is most commonly the case in the type of applications that I'm interested in studying, the continuous spectrum equation is distinct from the variance equation. And what we've actually identified is a discontinuity in the solutions to this equation. In particular, we have the case where our covariances have some sort of non-zero correlation length scale. The dynamics satisfy the variance equation, but that changes discontinuously to the continuous spectrum equation the moment that the initial covariance becomes strictly diagonal. And so this discontinuity that exists in the continuum covariance dynamics actually has very important consequences when it comes down to evolving covariance matrices in discrete space. And even though these strictly diagonal covariances, this white noise may not exist in practice, this solution and this behavior really makes its presence known in these discrete contexts, and it actually helps to explain these weird behaviors that we observed in these numerical experiments before. And so we can kind of get an intuition as to why this discontinuity in the continuum dynamics is actually a problem when it comes down to evolving covariance matrices in practice, by thinking about this formulation of discrete covariance propagation that I introduced before. So if we think about this sequence of matrix multiplication operations, we can think about this as a sequence of two steps. The first step inside these parentheses, you can think about as the actions of propagation information along the columns of the covariance matrix. And then when you take the transpose, you then have propagation of information along the rows. And so in this little schematic of the covariance matrix, we can think about how this propagation along the columns and the rows influences information along the covariance diagonal, which is what I'm interested in. And so it turns out that for standard spatial discretizations that are used to build this matrix M, this sequence of operations is actually using off-diagonal information to approximate information on the diagonal. And so in a simplified context, what is this doing? It is actually averaging across the covariance diagonal. And the thing to know is that you're actually averaging or approximating across a discontinuity. Because as I've just shown, there exists this discontinuity along the covariance diagonal here, but these methods are approximating across a discontinuity. And as mathematicians, you should be thinking, oh, that's a huge red flag. We don't want to be approximating across discontinuities. That's analogous to, approximating across shocks, for instance. And so this structure of covariance propagation is what is responsible for producing these inaccurate variances that we saw before. So this is a figure that I have shown before in this previous section of these numerical experiments. So just as a reminder, in solid black, we have the exact variance, and then these colored curves correspond to different approximations, and dashed this approximation from the diagonal of MMP transpose. Solid is what we get from these Monte Carlo approximations. And then for reference, this black dashed line here is actually the solution to the continuous spectrum equation in this context, which just happens to be constant. And so what we can see is that these numerical approximations do not approximate either the variance solution or the continuous spectrum solution, and are approximating something wildly different. And the intuitive explanation is that they are approximating across this discontinuity. But what I've been able to do recently is actually identify the explicit error terms that are causing this behavior by taking discretizations like this and actually deriving the dynamics that these numerical schemes are approximating. And we'll see very clearly why this kind of structure of covariance propagation is causing these problems. And so to answer this question, we want to know, well, what is MPM transpose actually approximating? And so what I will go through is in a illustration of this, again, for this one-dimensional examples that I just showed in the previous slide, to identify these explicit error terms that are driving these inaccurate variances we've seen before. So to do this, we'll remind ourselves, so in these numerical experiments, we're just living on the unit circle. And for this analysis, even though I applied a finite difference scheme to this, to the experiments in the previous slide, for this analysis, we can really just focus on the semi-discretization, so simply the discretizations in space, and leave time as a continuous variable. And so for this analysis, I'm going to consider the state equation written in this energy conservation form, and I'm going to apply just a standard second-ordered center difference scheme to these spatial derivatives. And so when you do this, you then end up with the corresponding semi-discretization for the state variable Qi. Now what we can do is we can then take this state semi-discretization, and then we can use it to derive the corresponding semi-discretization for the behavior along the covariance diagonal. So what do I mean by that? Well, first we can define this covariance quantity. So the ith element of a given time is defined here. We then use this definition and the semi-discretization for the state. We plug all these things in, do the appropriate algebra, which I will save for you. And then to get the diagonal, we restrict ourselves to I is equal to j. And then we end up getting the corresponding semi-discretization for the covariance diagonal. So the time evolution of the ith element of the covariance is given by this equation here. Now I've done a little bit of algebraic manipulation to try to make some behaviors kind of very clear in this equation. In particular, I have highlighted these terms in red. And if we look carefully at these terms, what we see is that these terms live on the immediate off diagonal of the covariance, and they are averaging across the covariance diagonal to then approximate quantities on the diagonal, because this is the evolution of, the diagonal elements, and these are averaging terms. And what we'll see is that we had an intuitive idea that that was going to happen from the structure, and now we see it explicitly here. Now we want to then see, well, what does this averaging behavior then produce when we look at the continuum dynamics this is actually approximating? And so we can take this analysis a step further, and we can do a very standard approach by using Taylor series expansions to derive the continuum dynamics that this semi-discretization is approximating. And so when we do this, we then expand all of these quantities to the covariance diagonal. I'm going to call that quantity P sub d for simplicity. And then I'm also going to introduce a new term, L, which refers to a correlation length. This is a correlation length scale that one can define using second derivatives of the correlation. But again, you can think about it just tells you how fast correlations effectively decay away from the diagonal. Now, pushing through several pages of Taylor series expansions, we end up them getting this equation here, which are the continuum dynamics that this semi-discretization is approximating along the covariance diagonal. Now, there's a lot of pieces to this equation that we can kind of parse. The first thing to do is that if you ignore all of the terms that I've highlighted in red and blue, what we have is the correct dynamics that are supposed to be approximated along the covariance diagonal, okay? Now, the terms in blue here that I've highlighted are the typical form of the error terms that you would expect for a second ordered center difference scheme. So they're ordered delta x squared and involve these third derivatives. So these are the typical error terms that we expect. What I've highlighted in red are error terms that are different from these typical discretization terms that are direct consequence of these averaging terms that average across the covariance diagonal. And in particular, these error terms have a very specific form. They depend on the ratio of our grid spacing delta x and this correlation length scale I've defined L. And so what one can imagine is that for a fixed grid spacing delta x, as this correlation length scale gets really small, these error terms become large. And as these error terms become large, they start to completely alter the dynamics that are being approximated along the covariance diagonal. And these terms are not typical error terms that you would expect from this centered difference scheme, and again, are a direct consequence of averaging across the covariance diagonal. And so we can verify that these dynamics actually produce those inaccurate variances that we saw in those numerical experiments before by just go ahead and simulating this equation. And so in this figure here, what I'm going to do is I'm going to show two examples of comparing these dynamics on the previous slide to what we get in these experiments. So in this figure here, it's changed a little bit. So in the black dashed, we have the exact solution to the variance equation, where each of these panels just correspond to covariances with different initial correlation length scales that are proportional to this constant C, which again should be the same for these two covariances. They shouldn't change. And then in solid black, we actually have what this MMP transpose, this discrete covariance propagation is producing, which again, we saw before, does not approximate the variance equation well and depends on these initial covariances. So in the first set of simulations, we can say, okay, well, what happens if we just look at the errors caused by these typical discretization error terms? And so if I simulate those dynamics I showed on the previous slide, where I drop those red terms and I only look at the typical discretization errors, we have the approximation that's given here in blue. And we can see that it approximates the variance solution quite well, but is not capturing what we observed when we propagate the covariance through this MMP transpose. But if we include those error terms that depend on this ratio of delta x in the correlation length scale, we get these red dot dash curves here. And what's quite remarkable is we can see that it actually captures quite well what MMP transpose is approximating numerically. And what this verifies is that it is not these typical numerical discretization errors that are causing these problems during discrete covariance propagation. It's actually something much deeper than that and is intimately related with this discontinuity in the continuum and this structure of MMP transpose approximating across this discontinuity. Now, you may be sitting here thinking, okay, this is probably very specific to the discretization scheme that you chose or the dynamics that you chose. But what's actually quite remarkable is that we get the same type of error terms for a different discretization scheme in a different set of dynamics, which again highlights that this problem is intimately linked with this underlying continuum structure. And so what I'll show very quickly is that we can consider a slightly different set of dynamics and get a very similar looking type of error terms in these equations. And so in this case, I'm going to consider a simplified set of dynamics where we're just going to consider the pure advection equation. So there's no 0th order term here. And we're going to do a very standard approach of applying just a first order upwind differencing, which is very common for this equation. So then we have the semi-discretization for the state, and then same procedure as before, we get the corresponding semi-discretization for the covariance diagonal. And the first thing to observe here is, like we saw in the second ordered centered differencing case for a different set of dynamics, we have a term that is approximating across the covariance diagonal, even though we're looking at a different discretization and a different set of dynamics. And so like we did before, we can go ahead and push through and find the dynamics that this semi-discretization is approximating. And what's surprising is, even though this discretization is quite simple, the number of error terms actually increases. But there are some similarities to what we saw before. Again, if we ignore all of these terms in color, we get the correct dynamics that are supposed to be approximated along the diagonal. Now, in blue, like before, these are kind of the standard error terms you would expect for a first order scheme. So these delta x terms with these second derivatives. And then now we have these other error terms. The terms in red that I've highlighted here are actually the same error terms that we saw in that second ordered center differencing scheme, which is quite remarkable. So we still have these error terms that are going to completely alter the dynamics that depend on this ratio of delta x and L squared. Again, for a different discretization scheme. Now, because of this first order scheme, we actually accumulate some additional error terms I've highlighted in orange that do appear in the second ordered scheme that get pushed up into higher orders. But the term that I want to point out in particular is this first term here, which is a order higher than these terms in red. It is a delta x over L squared term, which means that this error term is actually going to dominate in these dynamics in what we refer to as a 0th order dissipative term, because we assume our velocity is positive and then these diagonal elements are positive as well. So not only do we have these red terms altering the dynamics, in these first order cases, we have this very dominant dissipation term here. And so I'll just show very quickly, we can actually verify that these approximated dynamics do actually model what's happening in our numerical experiments. And I'll just show that very quickly here. This is slightly different, so I'm showing the same initial covariance length here, but now two different initial variances, just so there's something interesting to look at. So in this case, the solution just exact variance remains constant, but in this case, we have an initial variance that varies in space, so we have some interesting structure. And then in solid black, we have what MMP transpose gives on the diagonal. And then in blue, we have the simulations with kind of the standard error terms, which we see as dissipative, but is not dissipative enough. We actually need those additional error terms that I derived before in order to better capture these dynamics. And so what I've shown here in these very simplified one-dimensional examples is very illustrative of what is going on in these types of dynamics and actually helps to explain a behavior that has been observed in the chemical tracer forecasting community going back to the early 2000s. And so this is an example that comes from a work by Richard Menard and co-authors, where they're interested in modeling the transport of ozone along an isentropic surface of our stratosphere. And in these contexts, this ozone concentration is just simply modeled by the advection equation. And so there's a equation for the variance, and in their application, they take the initial variance to be 1. And so what this means is that the exact variance should remain 1 for all time along this surface. And what they found in their numerical experiments, when they propagate the variance using this MMP transpose, is that there was a significant amount of variance loss in the southern hemisphere that I've highlighted in this box here. And so if you look very closely, you see that actually almost half of the variance has been lost in this region. And going back to these experiments in the 2000s, people really didn't understand why they were losing this much variance in this region. Now, if we think about the dynamics, this southern hemispheric region is known as a surf zone, and there's actually very strong wind shear in these regions. And what the wind shear does is it elongates correlations along the flow of the wind shear, but then correlation length scales perpendicular to the flow start to shrink dramatically. And so what we're seeing here is that as these correlation lengths shrink, you get a dramatic loss in variance. And this directly corresponds to those error terms that I showed before. The explanation for why they've lost half of the variance here is not this normal numerical dissipation, but really is a consequence of this discrepancy between the way that MMP transpose is trying to approximate solutions and these error terms that pop up that correspond to this averaging across the diagonal. And so this analytical work that we've done in these simple numerical experiments really shed light on a problem that's been going on in these contexts, again, since the early 2000s. And so just to kind of summarize where we've gone in this journey, what I've been able to show by studying these two parts of this problem is that these standard methods of evolving the variance are inherently inaccurate for these types of advective systems. And the inaccuracy really arises from this gap between this discrete propagation, this structure of MMP transpose, and this behavior that we've observed in the continuum, this discontinuity in the dynamics that we've been able to identify. And so I spend a lot of my time and a lot of my research really focusing on trying to bridge the gap between these two problems, again, motivated by their application and their use in contexts like weather prediction and ozone forecasting and so forth. And so I'll just kind of conclude by looking at future research directions and some things that I'm interested in studying, having worked on these problems. And so one natural research direction that I'm interested in looking at is, can we perform this kind of analysis for different types of differential equations? So for example, what happens if we look at systems of hyperbolic PDEs, or if we even look at nonlinear equations, so for example, Berger's equation? Can we define covariance and variance dynamics, and what can we learn from studying these PDEs like we were able to learn by studying covariance PDEs for these types of equations? Another aspect that I think is interesting is also trying to design numerical methods specifically for covariance propagation. As I kind of alluded to in this talk, the common practice is to build a numerical method for the state, and then that then implies a propagation of the covariance matrix. And I am interested in actually designing numerical methods that target covariance propagation specifically, and have some ongoing projects that look at ways to do that. And then something very recently that I've been interested in is diving into a bit of machine learning, because we can take advantage of these machine learning methods that learn dynamics to try to learn covariance evolution equations from data. So we're actually very lucky that we have an explicit equation that defines the covariance evolution here. But it would be very interesting, and I'm very interested in learning about covariance evolution equations in much larger systems. And I think we can take advantage of machine learning methods to try to learn what these equations are from data. And so with that, I think I'll go ahead and conclude. I want to thank everybody. I want to thank Christian for the invitation to speak today. And here are the relevant publications that I discussed in this work. And I'm happy to take any questions either online or offline via my email here. So with that, thank you.
Thank you very much. It was a really nice talk. I'll applaud for all of us. I think we will go ahead and hit stop on the recording.